Sorry that I missed the actual meeting for the SOOS Polar AUV 2021 meeting, but there's some technical difficulties, and I'm here now to at least present what's been going on with Icefin. What I'll give, hopefully not too long of a talk. I'm going to try and be quick. With an overview of what happened in 2019 and 2020 in the field season, sort of talking through some work in progress, bring up some updates and some difficulties on instrumentation, and then I'll talk a little bit about what's coming up in the future. So I am Peter Washam. I'm giving this talk on behalf of the whole Icefin team, most of which have transitioned to Cornell University with our PI, Brittany Schmidt, some of which are still at Georgia Tech, but all of us kind of have this dual appointment for the time being. And for those of you who aren't familiar, below is a CAD image of Icefin. It's a hybrid, remotely operated autonomous vehicle, so it basically operates on a fiber optic tether. It's skinny and long, as you can see, so it can go through boreholes, through ice shelves that are drilled through hot water, or through sea ice with an ice auger, something like that. It has a bunch of instrumentation on the front: cameras, sonar, CTD, DO, as an optional setup right here, where it's either a multi-beam sonar or some combination of biogeochemical sensors. And then in the back we have this DVL, which doubles as an ADCP, and a laser altimeter, and on the back there's just some cameras and this thruster. So all of this work is a part of the ITGC project, as well as some other grants, a NASA grant, and an upcoming NSF grant that we're really excited about. So I'm going to talk through the work that was done in 2019 into 2020. That was at Thwaites Glacier on the eastern ice shelf here as part of ITGC, at the back of the Ross Ice Shelf, at the Cam Ice Stream, close to the Cam Ice Stream grounding zone, and then up front here on the front of Ross Ice Shelf in McMurdo Sound. So some of you might have seen some of this beforehand, so I'll just do my best to sort of summarize it in a brief manner. But here's the summary of the data at Thwaites. So the left here is showing the box of where the data was collected. So here's the eastern ice shelf, and these different colors are the grounding line as it's retreated over time to the point where it's now in sort of this shaded grayish blue region. And here you see the dives, the Icefin dives conducted in that region, and it's a summation of 5 dives that have been combined to make these 2 transects here, T1 and T2. So you see it's very chaotic in this region. The ice and the seafloor especially, there's lots of topography there, and the seafloor is sloping up towards the grounding line instead of back, as sometimes we think might be the case, especially for more like the main trunk of Thwaites. But here in this region, what we call the butterfly, the ice shelf is resting on kind of like a hump, so it's prograde here, and it will become retrograde at some point. But anyway, so the ice, there's all these crevasses and terraces and really interesting stuff, and the water is very warm and very exciting for us, and I think the community at large. On the second transect here, Icefin actually reached the grounding line point where the ice and seafloor make contact, so that's a big point of pride for us right now. So here's just the salinity to go with. I didn't talk about the temperature at all. It's quite warm. It's well above 2 degrees above freezing throughout most of the water column. It's salty, and then it freshens towards the ice base. And then we have this beautiful ADCP data set that I personally worked very hard on. And it was a joy. It was definitely a labor of love, but it's something that I'm excited that we now have the ability to record these very detailed currents at high accuracy at these very low current speeds. So here you see the color bar is showing currents between something like -3 and +3 centimeters a second. And in general, there's like an east-west flow here. So it's like into the page or out of the page. And, or sorry, it's a north-south flow. No, sorry, east-west. I'm getting confused with another site. But interestingly enough, this flow is parallel to the grounding line instead of perpendicular, which we think of in sort of typical plume models. So it's an inflow at depth and then sort of a buoyant outflow near the ice base. And when you look at a profile of all the data from these dashed lines here, you can see a good representation of how that looks. So maximum currents are somewhere close to 6 centimeters a second in sort of the bottom of this crevasse here. So this is a really busy figure and there's so much going on. I'll just kind of jump to the takeaway. We just took the temperature, salinity, and current speeds at different points near the ice base in different regions, and we made some assumptions here and then basically binned these regions of the ice base in the ocean. The ocean temperature, salinity, current had to be within 5 meters of the ice base. And yeah, so we took all of that and we threw it into this 3-equation melt parameterization, tuned our results to an AP res here and sort of backed out these melt rate estimates for this location or these two transects. So we're getting sort of melt rates from 0 to 2 meters on the flat stuff out here up to 20 or so meters per year, actually up to about 25 meters per year in these crevasses. And some of this has to be taken with a grain of salt. It's very much an estimate. In some regions, this estimate is really good. In others, it's it's less good. But all in all, this is very exciting, and we're able to sort of point out how the slope of the ice base is very important in dictating the transfer of heat and salt into the ice base and therefore the melt rate. Here's just really weird PDF of all that data that I'm not going to really go into much more than saying if you look at each of these transects, T1 on the left, T2 on the right, again T1 and T2, you see that most of the melting is happening at very sort of low melt rates along the flat ice, and then there's this sort of second peak of high melting along sort of crevasse walls and terrace walls. So the next site I'm going to talk about is the site at the back of the Ross Ice Shelf near Cam Ice Stream. So this is some work that Justin Lawrence is leading. He's a PhD student with our group. He's hopefully going to submit this paper soon. So this site was cool. It was somewhere between 3 and 5 kilometers from the grounding zone. And the ice was really weird here too. It's sort of got these concave features with these big crevasses overlaid on top. And then the ocean was this beautiful 2-layer system. And we actually swam Icefin. I was here for this field work, swam it into this crevasse here. I'll show you some of the results of that. And then here's all this really cool imagery from the ice and seafloor. Here's just kind of like a general overview of what the water column looked like there. There's this 2-layer system. This region's fascinating because it's got strong tides, but it has this background sort of buoyant, buoyancy-driven flow too. But for the most part, the water column was sort of varying with the tide, both in the stratification of these two layers, as well as the current speed here, which you can see there. And it all fits pretty much perfectly on the meltwater mixing line with concentrations of sort of 1 to 4.5 milliliters per liter of meltwater. Here's some of the data from when Icefin swam into that crevasse. This is something I've been working on. There's still a little bit of work to do to correct location, because when we were in there, we dropped a lot of DVL pings, a lot of a lot of DVL pings that was pointed downward this time. But anyways, we collected this really cool data set of the oceanography in this crevasse, and here we're able to look at the 3D current structure in the crevasse. So the predominant flow is into the page, so southward. It's that purple blob there at about 6 centimeters a second. And then you had this background overturning, which had to do, interestingly enough, with supercooling in the crevasse. So we passed this limit towards the top where the water transitioned to supercooling. And you see that well here, where there's a rising in the green here into the crevasse, and then a sinking back on this side with the purple data. And then there's this movement to the right where the water is sinking. So this is kind of like, we're very excited about this. I'm very excited about this because it's really pushing the boundaries, I think, of what we can do with Icefin. So here's just some profiles, some vertical profiles of what all that data looks like, and it took a good bit of work, but again, it's another example of how we're able to pull out these current speeds or these velocities at really high accuracy, even though we're in these relatively weak, quiet environments with not too much flow. And I think that's largely due to the fact that our ADCP is doubled as the DVL, and its error is a function of the vehicle's speed. And Icefin doesn't swim that fast. It usually swims at 50 centimeters a second or something like that. So we also did work in McMurdo Sound. I'm not going to talk about this too much, but we did it in this rift here. There's some dives that are shown there, which was at the front of McMurdo ice shelf. And then this is actually from 2018, but at sort of the grounding zone of Erebus Glacier Tongue. And here's just an example of some of the data that we picked up beneath the ice shelf in that rift. So the rift here, it's filled with all this crazy platelet ice. So this is the returns we got off of our DVL, but it's variable based on those platelets, and you see how rough the returns are because of that. But yeah, it's this rift that's about 3 meters tall, and the water's all super cooled in it, so it's actively freezing, which is cool, and also very difficult to work in for CTD, for good CTD data collection. So some more work in progress. We have multi-beam data from Thwaites. Brittany's working on that. It's been a little difficult to work with, but it's coming along, and here you can see some of the data from one of the dives, and you see there's all these really cool features in the seafloor from the grounding line or the ice moving around over the seafloor. And then we're also working on sort of these very detailed ice-ocean interactions where we're actually have this imagery of the ice base, which is cool. So here's like one part of the crevasse where there's these runnels, and then actually these scallop formations on top of it. And since we have the sonar, we're able to scale all these different features. So here you can see the runnel is between two runnels. Here's like a crest, and here's another crest. It's something like several meters deep, and then there's these little blobs poking out, which are the scallops. So we're working with that data to like get a really good read on the drag next to the ice and what it might be doing on the transfer heat and salt, and therefore melting. So just some instrument stuff. In 2019 and 2020, we learned that these grounding zone environments have particulate material everywhere, and we encountered a lot of problems with this with our conductivity sensor. We had problems with that before with sea ice, platelet ice formation in super cold regions, but here it was very prevalent, and it would just cause these little offsets in the conductivity sensor where it would still behave right, but it would step down usually to make it look like basically the water was fresher than it was. And we took a lot of time to correct all that with outbound and return dives. So that's just something we've learned that would probably be helpful for others who might be in these environments. You might expect something like this. And then interestingly enough, our software's navigation system makes the vehicle go in the wrong direction when you're south of 81 degrees. So at the campsite, we would take our heading and we would drive in a direction, and the software would basically keep the heading right, but it would move the vehicle in the opposite direction. So we worked around that. Our software engineer figured out an independent navigation solution that can update live. We got new batteries, we got a longer tether, which is exciting, so we can get longer transects now. I think it's 4 kilometers. It might actually be longer than that. We got a new RBR Legato CTD, actually 2 of them. We have a functioning water sampler that we can use now on Icefin, and then also a digital holographic microscope, and then there's just lots of other stuff that is less exciting that I haven't listed. So what's coming up? There's work back at the CAM ice stream grounding line. This is now, so KISS 1 was the data I showed there, and then KISS 2 is over here. And it's at this, the outlet of the subglacial channel. So the blue here shows the predicted subglacial water paths, the routing paths. So Icefin's going back down with our collaborators in New Zealand, and Brittany's leading